Okay, we're talking about particle kinetics today, and in particular, we're going to discuss the work and energy method. So what is work? We can say work is done whenever we have a displacement in the direction of applied force. So we have work when in the direction of applied force. So very briefly, we could look at what work looks like along a horizontal path. So let's use a different color. So work along a horizontal path. So let's say we're going from this position to this position. The origin is XA. The destination is XB. You have a particle that you're analyzing. It's being subjected to a force F at an angle theta, right? So that's, I think, all the important components we have for force and displacement. Let's now work in terms of energy and the work terminology. So in this context, you could say the change in work between A and B are F cosine theta XB minus XA, right? So you're looking at this force being applied over the entire trajectory. In this case, you have a horizontal path, and you multiply that by the amount of displacement that you are covering. So in this case, we have XB minus XA. And generally speaking, because you have newtons times meters, the units for change in work are usually Newton meter, or you could also express this as joules. If you're working in America, maybe you want to go with feet, pound. We generally avoid pound feet because that's a unit of moment. And we don't want to confuse moments with work and energy that we're talking about in this lecture. Okay, so that's work along a straight path. Let's now talk about work done by a spring. We're going to choose a different color. We have work by a spring. So in this case, I am going to draw a fixed base. We have our spring. The particle is attached to the spring. The spring has a stiffness coefficient of K, and we could say that the particle is being moved forward in direction X, right? So if it's going forward in direction X, the spring is going to naturally want to pull back. So X is pushing forward. The reaction force will be F is equal to minus Kx. So now we could use the force equation again. So it's basically UAB, this time for the spring. And generally speaking, we are looking at integrating force over the trajectory. So usually what we're interested in is XB, XA. So let's say we're going from A to B, right? We want to know what the force is along this trajectory, dx. So this is really a fundamental equation for the work and energy method. So we already know what the force is. Here we have XB, XA minus Kx, right? The force is in the opposite direction as the displacement. So we leave it as a negative, and we have dx. So this equals to minus 1/2 kx squared, and it goes from xb to xa. And so if I put the bounds in, what I end up with is minus 1/2 k xb squared minus xa squared, right? So what you're really looking at is you're looking at this force displacement trajectory. So you have force and displacement x. And the spring force obviously increases linearly with slope k. So this is k. And what you're calculating is this area between position XA and XB in order to get your change in work. So this entire area is what we computed when we calculated UAB. Now we can look at work of a weight. So we could say work of a weight. So how do we look at work that's done by weight? Well, it's very similar. You again have to assemble this equation, which is UAB. It has the integration of force over a trajectory. In this case, we're going to call it dr. I'm going to represent this schematically as well. So let's say, let's use a blue color. We have a particle moving in this direction. That's our trajectory. The smallest component of the trajectory is dr. We have the self-weight of the particle, which is w. And let's say we have a coordinate system x, y, and z. Okay, so in this context, what I can say is, oh, and by the way, we're going from some position A to some position B. You're always going from an origin to a destination. So in this context, what I can say is my integral has its two bounds, right? We have the two bounds. I can say my force is applied vertically in the downwards direction, so it's a negative because it's downwards, and we've already defined that y positive is up. So we have minus w. What's the unit vector in the y direction? We have j. So we have this. And then we want to multiply this by the trajectory. Your trajectory is going to have x component. It's going to have a y component. It will also have a z component. Kind of like this. And so since work is only being applied in the vertical direction because gravity is only up and down, we can ignore everything except for the j components. So what we end up with is yb, ya minus w dy. And really, mathematically, what has happened is we performed the dot product between the ijk unit vectors, and whenever the unit vectors are not matching, you end up getting a 0 because those are orthogonal to each other. So only when you have the two j's getting multiplied is when you end up with w dy. Okay, so that's it. We go ahead and integrate this. W is a constant. You always have a constant weight. So we have minus w yb minus ya. And so, w can also be expressed as mass times gravity. So we could say minus mg delta y. So we talked about the different kinds of potential energy. We want to now talk about kinetic energy. So with kinetic energy, again, you'll always have some kind of trajectory. You're going from position A to position B. You have some kind of velocity to begin with at position A, and you end up with another kind of velocity at position B. And this is your particle. At any point in time, your velocity is v, right? This is your mass, your particle. So what we could say in this context is that all your changes due to different forces over this trajectory, right? And this trajectory is x. So this integral, which is your change in energy or your work, summed over all the different works that are being done, is equal to the integral over the velocity of your mv dv. So it's mv is obviously your momentum, and we're looking at how the velocity changes in relation to your momentum. So going from A to B, what you end up with is 1/2 mvb squared minus 1/2 mva squared. So in this context, we could say this is the kinetic energy. By the way, kinetic energy, we use the term T to describe it. This is TB, and here you have TA, and these two are subtracted from each other. So if I move things around, what I can say is that my energy equation is, so energy and work equation is, it's whenever I start with some initial kinetic state or kinetic energy level, TA, then I have all this work that's done, UAB, and this whole thing gives me TB. So let's summarize. We have the different kinds of work and energy. We said you have kinetic energy whenever you have T is equal to 1/2 mv squared. So this was kinetic energy. We said we have potential energy. For potential energy, let's use V. So we have V gravity. For potential weight energy or potential weight work, we have mgy. So this is potential weight work. We have the elastic potential energy, VE is equal to 1/2 kx squared. This is potential elastic, I guess let's just use the term work. And we have two other things. We have external work that's being done. For external work, I'm referring to the forces that are new to the system. So they're modifying your system. So all those F's that we usually put on the particle. And we're going to use W to express this. So Wx is equal to Fx. So we call this external work, and it's applied over the trajectory x. We also have internal. So if you have external, we also have internal work that's being done. Usually internal work is all those frictions that are applied over the displacement trajectory. So we have mu n, right? Mu n is the coefficient of friction times the normal force, and this is multiplied by x again. So we call this internal work. Okay, let's do an example together now. So in this example, we have a block that is being, so we have block B that's being driven to the right at a velocity of 5 meters per second. There is a distance of 2 meters before a spring is impacted. So this is a spring that we have, and the coefficient of stiffness for the spring, this is spring A. The coefficient is 200 newtons per meter, right? And the mass is moving in the right direction. There is a surface friction, which can be described as kinetic coefficient of friction. Mu k is equal to 0.25. So we can write this down. And so you can think of this as mass A moving to the right side at a constant velocity. Well, it's not a constant velocity, my apologies. You're starting at an initial velocity. There's friction. So it's slowly slowing down. It comes into contact with spring A, compresses spring A, And what we want to find out is we want to find the compression in the spring. So determine the compression in spring A. So that's really the whole gist of the problem. By the way, MA here is 8 kilograms. So what I want to do now is I always want to start off with a free body diagram. So here goes my free body diagram. I have the gravitational components of the force. So we have 8 kilograms times 9.81. That's W. We are going to have a normal force that's applied. In this case, normal and W are equal, right? If we are moving in the right direction, that's the direction of velocity, we're going to have a friction force in the opposite direction, F of F, which is equal to 0.25, right? This is using the coefficient of friction times N. Okay, so we have this. Let's see. 8 times 9.81 is approximately 78.5 newtons. So here you have 0.25 times 78.5, like that. And so if we do the algebra correctly, we have 19.6 newtons. So these are all the forces in the vertical direction. What else do I have? Obviously, at the moment of impact with the spring, I will also have the spring force that's going to be in the opposite direction. Let's call this FSP. Okay, that's, I think, all the forces that we're dealing with. Let's put everything together. So we're going to have, let's see, we're going to have work that's done by the spring. We said we will use the term VE for elastic potential energy. When I'm moving to the right, my spring force is to the left, so the force and displacement are in opposite directions. So the elastic work is negative. So we have minus 0 x. So you're starting from 0, which is this position here, and we move into the spring, move in meaning we're compressing the spring by x. The coefficient is 200. The compression is x, so 200 times x is the F, and we integrate over dx, right? So this whole thing was FSP. FSP was 200x, and we multiplied by the trajectory. Okay, so we have minus 100x squared. If we do the integral correctly, hopefully we can see that we arrive at minus 100x squared. Okay, now we need to look at work done over the 2 meters where we have friction. So while the mass is moving to the right, there is some friction on this surface right here. So that's what we want to capture next. Here we have work internal, right? Internal work is mostly due to friction and drag. We have F of F, which is minus 19.62. Well, let's just leave it as 19.6. Here, the internal work is negative because you're moving to the right-hand side and your friction is pointed to the left side. So your force and displacement are, again, in the opposite directions. So we have the distance we have covered that we need to multiply by. We obviously have the 2 meters, right? This is 2 meters plus the x that we're compressing. Okay, so that's good. what else are we looking at? We have to look at the initial kinetic energy and the final kinetic energy. Initial is position A, so TA. We have 1/2, it's 1/2 mv squared, right? M is 8 kilograms, and the initial velocity was 5 meter squared. Then I have my final kinetic energy, TB. It's 1/2, 8. My final velocity when it stops, when the compression is maximum, is when the velocity is 0, right? That's when the mass stops. So we have 0 squared. So this whole thing is 0. And lastly, we have to put everything together. We have TA plus VE plus W internal is equal to TB. And down here, we call this UAB, all the work that's done from A to B. So we put all of this together, and we're going to the new page. We'll end up with 100 x squared plus 19.6 x minus 60.7 is equal to 0. And you have a quadratic equation. You solve for the positive root. So we solve for positive root. You kind of have to ignore some of the roots whenever you have a quadratic equation in this course, because they correspond to values that don't make physical sense. So we just ignore those. So lastly, we have x is equal to 0.68 8 meters. So now we're going to talk about the conservation of energy. So in order to really understand the concept of conservation of energy, we have to look at two types of forces. We have to look at conservative forces, and we have to look at non-conservative forces. Conservative forces are ones that are path independent. Or let me express this in the context of work, right? So whenever you have conservative forces, work done is path independent. For non-conservative, it's the opposite. It's the same stuff, but it's path dependent. With conservative forces, mechanical energy is conserved. With non-conservative forces, mechanical energy is not conserved. And so, of course, when we talk about conservation, we have to talk about reversibility. When you have conservative forces, work done is reversible. And for non-conservative ones, work done is non-reversible. And so what are examples of each of these? Well, let's say we have this trajectory going from A to B, and this one is a straight line, and this one here is a squiggly line, and this one is also going from A to B. So in this case, if you think about gravity and work done due to gravitational potential energy, so we can call this VG1, and this is a mass going down this slope, right? This is VG2. So gravitational potential energy in this case is conservative. It's a conservative type of work because it's path independent. So VG1 is equal to VG2. But if I am, for example, thinking about something like friction, this path is going to be shorter than this path, right? So the amount of friction that's imposed on the particle will be different. So your Wi1 and your Wi2 will not be equal because they are path dependent. So that's an important concept. We can also say that the total work done on a system, so that's the net work, is equal to the conservative ones and the non-conservative ones combined, right? What's the net work done on a system? Well, this is the change you have in your kinetic energy. So that's delta T. So it's T2 minus T1. What's the conservative work done on a system? Let's call this minus delta V. So that's your change in potential energy. And everything else here is all the forces that are applied. All the external and internal force times displacements, right? Those are the non-conservative works. So suppose this part here is equal to 0. Then we end up with the notion of the conservation of energy, which is basically T1 plus V1 is equal to T2 plus V2. And this equation is kind of important. This is an important equation. We call this the equation for conservation of energy. Conservation of energy. So it's a good idea to do an example with conservation of energy as well, where we don't have external frictions or forces being applied. This is applicable to a lot of different mechanical systems. So let's do an example. So suppose we have a mass that is sitting on a spring. So this is our mass. It has a weight of 30 pounds. It's sitting on a spring. What I decide to do is I take this mass from position 1, I squish it down to position 2, and then I let it fly up. So it flies to position 3. K here is equal to 100 pounds per inch. And the amount we push down is by 5 inches. So the question you want to answer here is, how high does the mass fly? And right now, it's a good time to pause and think about what this question means. So you push the mass down into the spring. Some potential energy builds up that's ready to release. As soon as you lift your arm off, the mass is going to be thrown up. So it starts off with some velocity, goes up, goes up, goes up. And as soon as velocity reaches 0, that's where it attains its maximum flight height. So this is the, what are we calling this? We're calling this H max. And then, of course, gravity is being applied, so you begin to fly back down. So the next question I want to answer is, are there any non-conservative forces? So are there any NC forces? Well, we're ignoring air drag. We're ignoring any sort of frictions that exist within the spring. And there is no external force being applied. We're pretty much analyzing after the arm is lifted. We're analyzing from position 2 to position 3. Yeah, you could argue from 1 to 2, some force is applied, right? So we're just applying, we're analyzing from 2 to 3. So we could say no conservative forces, no. Okay, so we can also draw a free body diagram. So that's our mass. We have W, which is 30 pounds. We have the spring force, which is going upwards. It's equal to 100. That's 100 being the coefficient of stiffness, and times 5 inches. That's 500 pounds. So I can use the equation for conservation of energy, which is T1 plus V1 is equal to T2 plus V2. So the initial velocity is 0, so we have 1/2 m v naught squared. This is 0, so this whole T1 is 0. At V1, we have 1/2, 100, which is the stiffness, 5 squared. So that's the elastic energy of the spring. We can say that position 2 is our datum. That's where potential energy is measured from. So if it's measured from there, then the height is 0. So Vg is also 0. And we have, this is equal to 1/2 mv1, so that's your final velocity squared. We said that at h max, your v1 is equal to 0, so this is also 0. So this whole thing is 0. We have a plus, so now we have to analyze v2. Oh, by the way, to avoid confusing you, these are capital V's and these are small v's. So don't confuse those two. These are velocities and potential energies. So they're two different things. Okay, so now we're looking at capital V2, which is the potential energy of the final state. So here we have mgh for potential energy due to gravity. And we don't have any elastic energy because the mass has already flown off of the spring. So the spring is no longer exerting any sort of meaningful force. So this is VE2, which is 0. Okay. So I already know what mgh is, or excuse me, I already know what mg is. Mg is equal to, let's see, 30 pounds. It's 30 pounds. And so cleaning things up a bit gives us 1/2 times 105 squared is equal to 30h. And this is h max, the maximum height of flight. So 1250 is equal to 30 h max. And if we do the math correctly, h max should equal 41.67 inches. And that's it. That's the maximum height of flight before the mass begins to move downwards due to gravity. All right. So hopefully you found this to be useful, and I will see you next time.